Nice to see everyone. Yeah, we're going to tell you our story about building the TreeScout. You're seeing the TreeScout on top of the tractor. We've built it to help apple and pear growers with precision farming. And we're going to explain you in this talk what it is, some of the challenges, and how we're scaling right now, because we're quite proud of bringing a product from nothing to now a product that needs to scale. So how cool is that? Yeah. But first, a quick introduction of us.
Yeah, so I'm Sebastian. I've been with Aurea for the past 5 years. I'm one of the senior software engineers on the project, responsible for, well, at this point, practically about every part, or part of every part of the system, from the device side to the cloud to our DevOps practices and beyond.
And Wieneke, the CTO of Aurea Imaging, joined to make this a really awesome product. But it's not the story of just the two of us, so that's why I also have a picture of the whole team. And this picture is also really nice because if you look, we all have very black feet. That's because we are an agricultural company, so we're with our feet in the mud. And we took that literally because we went for Wadlopen. So you can walk in the Netherlands in the North Sea, the Waddenzee. So that's a nice thing. We're not only a technical company with only software engineers, but also people who are actually mounting the system on tractors. We go quite often in the field, so it's a wonderful combination. But the first thing, if you really want to understand our use case, we just start with a non-technical part, and that is, I just want you all to think a little bit like an apple grower. So it's a quick course, only 5 minutes, don't worry about being an apple grower. So the first question is, which apple is the best? The middle, hey.
You've seen us before, haven't you?
Yeah. No, it's right, the middle one. And that's because if you go to the supermarket, you all see same size apples. And guess what? That's not how apples grow. But that's what gives the most money for the grower. So he wants to have the perfect size apples because he can sell that to the supermarket, and it gives him about 30 cents per kilogram more profit, which is quite a lot if you have that many apples on your trees. So he really want that. So guess what? You didn't know, but size does matter, especially for apple growers. Then the next question, which tree is the best? No, it's somewhere in the middle. It's also that. No, because you need blossoms to grow apples, and based on the number of blossoms, the tree needs to divide its energy over all the blossoms. So if you have many blossoms, you will have small apples, and if you have a low number of blossoms, you will have big apples. It's that simple. So a grower wants to have the optimal amount of blossom on each tree, and then he gets the most money from his orchard. You're still going to be an apple grower, so it's good to know that the blossom season is, especially from technology perspective, quite challenging, also from farmer perspective, because did you ever try to see blossoms when you think, oh, it's nice, I want to see a blossom tree? It's just not going to happen because it's only stay there for 1 week. And exactly in that week, you need to make sure that you get that optimum number of blossom clusters, which is challenging for the grower because in 2 weeks or 1 week, he needs to make that happen. So this challenges is a couple of years ago is where the mission of our company comes in. So it's really to unlock the potential of every tree, because traditional orchards, they just treat the whole orchard the same, because they didn't have a way to treat it per tree, because there are 2,000 trees on 1 hectare. So you cannot do just on vision, treat each tree different. It's just not doable. So with our technology, we really want to help the grower to have that. Who needs to wake up? No, it's really to help the grower with giving every tree what he needs. So it's beneficial for the grower, as well as it's more sustainable because he can use less chemicals and also less fertilizers, because he only gives it to the trees that really need it instead of all. Well, so we had a problem, we had a vision. The next part was a system. So we came up with a TreeScout. You see it over here. The TreeScout is a device. It has an onboard computer and 2 stereo cameras. We're collecting images, we're processing them on board of the machine, And we also have in the onboard computer a 4G modem, Wi-Fi, to send all the data to the cloud. And the idea here is a little bit visualized there in this video. When you drive through your orchard, you detect, and we only send detections up to the cloud to minimize the data. So we're not sending all the images because that would never fit over 4G or no internet at all in the orchard. And then we analyze the number of blossoms per tree. You see also the terminal with the TreeScout. Most growers already have that terminal because we're using precision GPS as well. So we're getting the precision GPS feed from the tractor because he also uses it to spray and for other applications. So quite often he already has a GPS with such a terminal, and we just make sure that he can operate also our device from the terminal, and that we use the GPS signal from the external GPS, which gives all kind of nice issues because integrating with GPS systems is not that easy as we would like to have it. A little bit about process. Just to highlight, Aurea Imaging is not focusing only on blossom because there are other characteristics throughout the year which are really interesting to know. So we have 3 apps on our TreeScout: blossom, vigor, that is how fast is the tree growing, and fruit count. And they are all you can use for different use cases. So you can, for example, if the tree doesn't grow fast enough, you can give extra fertilizer. If it grows too fast, you can do root pruning. You can use the number of fruits on the tree to schedule your logistics. So we give lots of data, and the grower can use it for different use cases. And how does that look like? So first he drives through his orchard to collect the data. When he's done, he goes to our portal. There he sees with the red and green squares the blossom score per tree. There you can look a little bit, okay, what is this year my optimal blossom number for this field? He selects that, then he exports the data, and that's also agriculture to a USB stick. He plugs that in his sprayer, goes again through his orchard, and then he sprays every tree with too much blossom. This is one of our most important use cases. And then a little bit about the numbers of how we are growing. And Sebastian will explain later on this talk more about how we are managing to grow that fast. Some highlights: you see the first year, 2023, that was our beta season. We failed horribly. As you see there, the time to deliver results to the grower was a month. And I just explained that blossom only stays for 2 weeks, so it was useless. Yeah, so we kind of rebuilt it, and the next year, with the same number of customers, we were quite happy. It worked awesome. Now, and from that time on, we are scaling quite constantly. And you see also that the challenges are shifting a little bit. This year, we made a big step in the processing time for the map. So he now only needs to wait 5 minutes before his data is ready. Well, last year, it was 24 hours, which we thought was good, but the grower didn't agree. He thought that was way too long to wait. That about the numbers. Then I have a short movie just to show how blossom thinning looks like. So what you see here, it's a 3-row sprayer. So he sprays 3 rows at the same time, and with the blue light, you see the sprayer goes on and off, and that is based on, we call it a task map, so that's based on inputs from our maps. And growers are actively sharing those movies with us because they love our product. So during the season, we are flooded with movies with all kinds of music, driving tractors. Look how nice! Look, it's working. So that's quite nice to see. But it gives a little bit of an idea how it looks like. Then before we go really into technical solutions, I thought it's also nice to share a little bit of our data quality issues, because if you're outdoor and you're trying to train models, it's not pretty easy. So for our blossom model, if you look, you can quickly see what's going wrong. It's detecting a cloud as a blossom. I did some blossom annotation myself, and I do understand why he thinks it's a blossom, because it's quite hard to detect a blossom. Here, this is one of our interns. He learned quite fastly. He learned 2 things. One, don't pretend to be a tree. And the second thing is don't wear white shoes in an orchard, right? You shouldn't do that at first place because they get very dirty. So, but when I saw this picture, it made me smile. Like, oh, that's so nice. We're doing, besides blossom thinning, we do also tree detection, because the first step is knowing where the tree is in the field. So this is a detection of that. What you're seeing here is we trained it quite good, but apparently it also thinks that shadows of trees are trees. This is all easy to fix. And then also a sneak peek in our office where we test a lot, and we need to be inventive. So what you see here is we have a tower with all TreeScouts, and they're all looking to the wall. So you see there a string of fake blossoms. It's quite nice because it also detects fake blossoms, and a string of apples. You cannot see it very good. And the nice thing of this picture is it's not detecting the string of apples we use, but it detects the string of apples my colleague is holding. So we were thinking, oh, okay, apparently, I think it's because he's black, you know, that it's looking more like a tree. But it's fine, we fixed it. So these are some detection things, but then we also have user behavior, which is always not so nice. This was a grower who really liked to work in the evening, but it's not working for us. Here we have someone who probably did some spraying before and then used a TreeScout, so the lens is really dirty. It's also not helping. This is Speedy Gonzalez. He drove really, really fast. It's giving us some blur. It's not helpful. And recently, we also have some TreeScouts in the USA. And we found this field. Apparently in the USA, they like to, I still don't know exactly why, but they put some white tarps under the trees, and our model fails on that. So that's a little bit about our data challenges we're facing. And now Sebastian will tell you a little bit more about how we are scaling.
Yeah, so now that you know all about, excuse me, agriculture, let's actually jump into the technicals of all of this. So, obviously, agriculture, thanks. Agriculture, you all know, highly seasonal. Sometimes, indeed, during the blossom, some seasons last for a good chunk of the year. The actual growing season lasts from April until about August, September, then it's harvest time. But some seasons, like the blossom season, only last a week in any given area. So you have to be able to really do the work, deliver results 100% of the time with accuracy the first time around. You cannot lose data because conditions change by the hour, and there's huge amounts of data coming in. TreeScout runs at 10 frames per second. Each frame can contain 100 plus detections. Now add that up across a fleet of 60, 70 devices. That's a lot of data. This year, those numbers that Wieneke showed for the number of images and detections, that was just the month of April. We ingested 1.6 billion detections in just the month of April. And we have zero opportunities to redo it if we get it wrong. So, yeah, it's got to work, at least during that 1 week, 100.0% uptime. So, let's get into it, shall we? So this is where we started. Pretty basic architecture. Each TreeScout sends its data over MQTT to AWS IoT Core. This is an MQTT service offered by AWS specifically for IoT and edge devices for communication with generally at least once semantics, and I'll get into that in a bit more detail later. From there, it's transported over HTTP to our actual cloud backend, which is run on Fast API, because of course we are a Python shop. That's all we do. There are no Rust components. There are no C++ components. If you want Rust, there was another talk about that earlier. From there, it's dumped straight into RabbitMQ. We don't do any synchronous processing on the Fast API side to achieve maximum ingest rate and maximum reliability. And in RabbitMQ, it's dumped into first MongoDB and then into our processing pipeline. And there, of course, it's processed into those nice maps that Wieneke showed earlier for the grower to use. And this worked well enough while our scale was still small. But it started to break down. Loading these big data sets for processing later through Fast API was slow and tended to overload during busy periods. That was why we had such big queues during the 2025 season was that they were just backing up on the database load and the HTTP server because, the GIL blocks everything. Fun. So what we moved to this year, what we spent a lot of time on before this year's Blossom season was actually the introduction of Apache Iceberg. So now the ingest is still first through Fast API into RabbitMQ and into MongoDB, but then there's an intermediate step where we take the data out of MongoDB, which is basically just used as a buffer now, and dump it into Apache Iceberg. The reason we use the MongoDB buffer is that it is basically to enable a batch write to Iceberg for faster reading later. Individual MongoDB writes are nice and fast. Individual Iceberg writes can be nice and fast, but if you have enough of them, your read is awful. So what we do instead is we batch it up, dump it into Iceberg as a unit, and then do the processing from there. And the read from Iceberg is nice and fast. We can load millions or even hundreds of millions of data points in seconds rather than minutes like it took before. And that was already a huge advantage. And because it's based on a cloud bucket, in our case, Google Cloud Storage, it also scales a lot better. So don't worry, I'm going to break this down in a bit more detail because there's more to it, of course. This is what it actually looks like in practice. So this is sort of really our bread and butter. I'm going to say we auto-scale a lot. Just about everything we have here, except the Fast API bits, is on an autoscaler because it's all RabbitMQ based. If you're used to an event-driven system, or let's put it this way. You're wondering right now, where is Airflow? Where are my DAGs? This is a data pipeline, right? Well, it is, but it's an event-driven data pipeline. We opted for that very early on because we realized that scales a lot better and a lot more easily. It's easier to separate concerns because there's multiple parts of the system, each of which has different interests. It's all one data pipeline, but we can structure it and scale it independently and make changes to it much more easily independently. So on the left side, we have, of course, our Fast API ingest. We scale that basically by hand still. That's something we're still working on. All that does is take the inbound data and dump it into RabbitMQ. That's served by an auto-scaled bunch of queue consumers. What they do is, they just take that data, dump it into MongoDB, and set a timer in Redis, a 5-minute timer. The reason for this is we don't actually know when the tractor's done. Because the device can drop offline, because the grower can shut it off, we don't have a done message. All we have is, hey, we haven't seen any more data in a while. We assume you're done. We're going to start the processing chain. So after that 5-minute timer is up, we take all of that data that we dumped into MongoDB, stick it in Iceberg. Again, done as a single batch operation. This generally, for a long drive, takes a couple minutes at most. So nice and fast. It's not prone to piling up, and there's still some optimizations we plan to make there as well. There's only ever one of these. And the reason for that, of course, for those who here has used Iceberg before, let's start with that. Okay, so bit of background then. Apache Iceberg is a data lake. It's based ultimately on some underlying bucket storage technology, in our case, Google Cloud Storage, though S3 works as well. And the idea is it stores Parquet files in that bucket along with some metadata about schemas and indexing. And then to write that data, you generate your Parquet file and upload it to the bucket, and then update schemas and snapshots. Problem with that is you can only do one write at a time. It absolutely hates concurrent writes. This is a known weakness of Iceberg, but it still doesn't actually affect scalability all that much as long as you're smart about it. But the trick is, if you can't do concurrent writes, your write worker, there can only ever be one of them. So once we've done that dump into Iceberg, we move on to the actual processing chain. What we do first is we take all of the drives across a specific field on the farm over a given day and aggregate them together into a single larger unit. And that's actually the processing unit for generating maps. The reason for this is you can have multiple TreeScouts running in the same field on the same day. You want to generate one cohesive map from that, not 2, not 5. Or the grower might drive part of the field in the morning, part of the field in the afternoon. Same idea. And then from that, we take that bigger aggregated collection of data and turn it into an actual result set that we store back in MongoDB and then serve up to the grower over Fast API again. And we can generate further downstream analytics products from that as well. And all of this stuff downstream of the Fast API, because it's all RabbitMQ consumers, it's very, very easy to auto-scale on queue length. All you have to do, take your queue length, multiply by whatever scale factor you want, and away you go. For this, because we're in the Kubernetes ecosystem, we use a tool called Kada. That's the Kubernetes event-driven autoscaler. Those veteran Pygrunners might remember a talk here, 4 or 5 years ago, where a guy introduced it. That's where I picked it up, and that's where we've been using it ever since. Oh, yeesh, dry air in here. And the result of this is that every single part of the pipeline is able to scale independently depending on how much demand there is for every part of it. If we have, let's say, 20 tractors driving at once, the ingest is busy, but none of the downstream stuff is going yet. Likewise, if everyone finishes at once, the ingest slows down, all the analytics stuff scales up instead. What this really enables is cost saving, especially at night. We scale, during the busiest period during the blossom season, we scale to about 6 times idle in terms of compute capacity. And overnight, we scale back down to just that idle state as well. But this really enables us to make that balance between huge compute capacity when we need it and cost savings when we don't. There is always some stuff running around when we're idle. Of course, you can't auto-scale an HTTP server to 0, but all the RabbitMQ stuff, because it's a queue, you can scale down to 0 when you don't need it, and it'll start right back up the second you do, or, well, at least a minute or so after you do. So, where does that leave us? Well, what did we learn from all of this? Because it's been a process. Obviously, we've got a few years behind us. The iceberg thing is new, but what have we learned building this overall architecture? First off, big data does not mean big architecture. You get loads of people out there saying, hey, you need complex tooling like Spark and Airflow and all of this stuff to build big data pipelines. No, you don't. If you know event-driven systems, if you know how to auto-scale, if you know how to separate your concerns between the components of your system, and you know how to do domain-driven design, like that talk this morning talked about, you can build it very simply, and then only introduce the complex tools when you really need them. And that's what we've done here. Is we've skipped the big complex data tools. We've kept it back to basics, and it still works really, really well. We're able to deliver results very quickly, on demand, not as a batch job because that's too slow, but when the grower needs it, when the grower delivers the data. And you don't need a big team to do this either. We're 9 engineers, and Wieneke, sorry. And that's all we've needed to actually build this and make this go over the past few years. Autoscale. I know I've harped on this a bit. I know I've harped on this a lot, but really, this is at the core of how we're able to do this without breaking the bank. There's only so much compute in the world. There's certainly only so much money in our bank account. The reality is, we don't need that compute 90% of the time. But when we need it, we really bloody need it. So, we autoscale and adjust our autoscaling metrics constantly to better match our compute needs and compute spend to the actual amount of data coming in. And again, all of this, and could we maybe save some compute by moving to Rust? Maybe. We don't need to. With the autoscaler, we can kind of have our cake and eat it too. All of our stuff is built in Python, nice and fast to build on and iterate in Python, efficient enough to meet the grower's needs without breaking the bank on compute. Yeah, performance testing. After the mess last year, where we actually nearly busted our SLAs on this one, because during the Blossom season we promised 24-hour delivery, we did a whole bunch of performance testing to identify the weak points in the system, both before and after we added Iceberg to the stack. Those performance tests that we did before the Blossom season, after we added Iceberg, looked great. And then the Blossom season actually started over the Easter weekend this year, and we had about 5 production outages in a row. The reality was, our performance tests had missed stuff. They had missed crucial paths, crucial flows, black swan data sets that the growers were generating, or strange user behaviors. And the result was this was jamming up the pipeline in places. Like you had that one worker to write from MongoDB to Iceberg. What happens when that worker runs out of memory? On a loop. Suddenly the whole pipeline jams up, that queue keeps growing, and no maps get processed. That sort of thing over and over again. The fixes were easy, but we hadn't been able to predict this in advance because our performance testing had missed stuff. So you absolutely should do your performance tests, but interrogate them constantly. Check your assumptions, validate your assumptions, make sure you're hitting every path and every corner of your system. And finally, be an engineering team, not a data team. We are a company that does data. We do a lot of data science, but we are not a data company. We're not a data science company. We're ultimately a software company. We build like an engineering team. We use pandas, we use polars, that's true enough, but there are no scripts in production. The data science people don't push to production. The data science people build stuff that gets integrated, unit tested, treated like real engineering products, and that's what goes to production. That's why it works reliably and scales efficiently. And that's basically it. Obviously, we've got a long way to go. It's a startup. The work is never done. And we've got a long way to go before we conquer the world. So yeah, We haven't talked about the device side as much this time around. Those of you who were here last year or who want to learn more about the device side, I welcome you to watch the talk we gave last year on the subject where we broke down the device side architecture in more detail. But yeah, we have some device side challenges still. Our fleet is now 65 devices, almost 70 devices in 7 countries, including some really overseas in the USA. How to keep them up to date. You can't send out a field technician every time you want to do a software update, but you don't have to if you're using Kubernetes on the edge. And that's why I encourage you to watch our talk. We have a huge load of third-party drivers and closed source software because of the nature of the hardware and the stack we use. Those cameras, I'm just going to repeat the four most feared words of every software engineer. Third-party hardware drivers. Yeah, that's been one of our biggest challenges for going on 2 years now, and it's only now drawing to a close, slowly. And then scaling up our geodata analytics even further. We now have several growing seasons worth of data for some of our old customers. How can we leverage that? How can we give the user more insights, more products based on what we already have? That move to Iceberg is a big step in the right direction because it really lets us play with the data in a much more granular and much larger scale as well. And then finally, yeah, right now, all of our installations are in the Northern Hemisphere. You know, 1 growing season per year, but that's not always the case. There's plenty of fruit growing regions in South Africa, Brazil, New Zealand, and eventually we're going to have to move there as well and move past sort of having a winter dead season and having a spring busy season to the point where we're actually busy year round. And that's basically it. We are hiring, so check out our LinkedIn page or give Wieneke an email. Now we've got, 10-ish minutes for questions, sarcastic insults, whatever you guys got. Let's hear it.